Team 24044, Wind Tunnel Launch Vehicle Aerodynamic Testing, sponsored by Northrop Grumman. I'm Savannah Shaw, and I'm majoring in mechanical engineering. I'm the team lead.
My name's AJ Sandler. I'm majoring in aerospace engineering, and I'm the aerospace lead.
I'm Connor Raskin. I'm majoring in mechanical engineering, and I'm the mechanical lead.
I'm Alex Daly. I'm majoring in electrical and computer engineering, and I'm the electrical and procurement lead.
I'm Oscar Lopez. I'm majoring in electrical and computer engineering, and I'm the programming lead.
Northrop Grumman has enlisted us to build a subscale, subsonic wind tunnel to test nose cone geometries at the Chandler location. Our wind tunnel must go Mach 0.5 with variable wind speed settings, have smoke trails for air visualization, and numerous sensors to acquire data for further analysis. We've had the unique experience of traveling to Chandler to present in person and tour the facilities. That is where our wind tunnel will go following design day. AJ will now take us away with the system requirements.
The fan speed shall be adjustable in order to vary airspeed inside the test section. Live data for airspeed and temperature inside the test section shall be displayed. Temperature and wind speed data shall be stored in a CSV file. Airspeed within the test section shall reach at least Mach 0.5. Smoke trails shall illustrate the airflow over the nose cones during testing. The wind tunnel shall have an emergency shutoff switch that will cut all power from the mechanical devices in case of emergency. The angle of attack for a test object is changeable between tests. Video shall be acquired of the test object and stored for playback. The wind tunnel shall be less than 15 feet in length, and the weight of each separable section shall not exceed 250 pounds.
The previously mentioned system requirements are what this project will be judged on and what needed to be met in order for the system to function as intended. Therefore, the system requirements had to be at the forefront of the design process. Being a wind tunnel, the most important requirement was reaching the minimum airspeed of Mach 0.5. To ensure this minimum airspeed was reached, the team performed a mass flow rate analysis. Another important requirement was visualization of the airflow around the test object. In order to do so, the team designed a smoke generation system. As we designed a wind tunnel that met each system requirement, we also considered potential risks to the functionality of the wind tunnel. The most important of these was turbulent airflow. To reduce turbulence, the team designed a nozzle with curved geometry to promote laminar flow as the air enters the test section. Also implemented were two flow straighteners to filter out turbulence as the air enters the test section. Other potential issues considered were foreign object debris entering the wind tunnel, weight as the wind tunnel had to be transported to Chandler, and an emergency shutoff switch for safety.
Here are the analyses we conducted to design our wind tunnel. A mass flow rate analysis was performed in order to determine the key dimensions of the test section and nozzle. Since air is considered compressible at speeds above Mach 0.3, constant volumetric flow rate could not be assumed. Therefore, using constant mass flow rate with Bernoulli's equation and comparing the test section to the diffuser outlet, the cross-sectional area of the test section was found as a function of the specifications of available fans and the desired airspeed of Mach 0.8. Once the side lengths of the test section were determined, a second mass flow rate analysis was performed with the nozzle inlet being compared to the test section in order to determine the necessary nozzle inlet dimensions. The results of this analysis were incorporated in the design and validated by CFD analysis, which will be shown shortly. Additionally, a structural analysis was performed on the test section to ensure that it could bear its own weight. The analysis yielded positive results with a safety factor of 1.8, even when overestimating stresses on the structure. The results of this analysis have been validated as the wind tunnel is able to stand on its own.
Seen here are the airflow trajectories. On the right side, inside the diffuser, vortices can be seen heading back towards the test section. However, none of these vortices are entering the test section and are of no concern during testing. Below, it can be seen that over 2,500 iterations were completed. The average maximum airspeed Mach number inside the test section was 0.74, with some iterations calculating an airspeed of over Mach 0.75.
Here's Alex with an electrical system overview.
Here's the electrical subsystem of our wind tunnel. The Arduino receives power from the computer. In turn, the Arduino supplies 5 volts to the pressure sensors and 3.3 volts to the temperature sensor. The first component the Arduino interfaces with are the differential pressure sensors and pitot tubes.
The air that enters the pitot tube from the front port is stagnation pressure. There are small holes on the side of the tube that measure static pressure.
The pressure difference between travels through the tubes into 2 separate ports on the pressure sensor. The sensor outputs the pressure readings as a respective voltage value. This means the voltage output of the sensors are connected to the analog input pins on the Arduino. The computer then converts these analog readings to digital readings via an analog to digital converter. These digital values can then be used to measure the velocity of the air inside the test section. The second sensor interfacing with the Arduino is a temperature sensor. This sensor is an integrated circuit that takes digital readings. Therefore, the sensor connects to the digital input pin on the Arduino.
Here is the verification that each system requirement has met. The voltmeter allows for the fan speed to be adjusted, thereby changing the airspeed in the test section. Additionally, the voltmeter has a shutoff switch that will be used to quickly shut off the system in case of emergency.
From the command window, we're able to launch the user interface. Simply press the start button to run a test. As you can see, it displays live data of airspeed and temperature inside the test section. In addition, the velocity of both pitot tubes is graphed live. To end the test, press stop. The data automatically populates into a CSV file in the desired file location. The serial data is populated into its corresponding column.
Preliminary research and analysis indicates that the speed inside the test section should reach a speed of Mach 0.5, which will be measured using the pitot tube electrical system. This is the smoke generation system, which consists of a fog machine pumping smoke into a reservoir, which is then fed into a manifold to create streamlines in the test section.
This is the test object mounting stand. As you can see, the angle of attack and the nose cone geometry can be changed between tests.
Northrop Grumman has provided us with a camera to use to video the smoke trails during testing. As can be seen here, the length of the wind tunnel is less than 15 feet, instead measuring in at about 9.5 feet. Lastly, the weight of the full system is less than 250 pounds, indicating that no one section weighs enough to invalidate the system requirement. Here's Oscar with lessons learned.
The experience gained from this project has been invaluable in preparing us to work in the engineering fields. These lessons learned include internalization of the design process, perfection of documentation, technical writing, presentation, working as part of a multidisciplinary team, communicating with vendors, and dealing with fate. Major issues our team encountered and dealt with were some issues with our vendors and the budget. We therefore learned to always request full documentation from any vendors and to have a backup in case they falter. Also, we found that it is our responsibility to catch any budget discrepancies. The team saw this project through, from the initial planning stage all the way to the end product. This unique challenge allowed us to experience a wide variety of scenarios and engineer encounters in the workplace, truly prepping us for the world we're entering after graduation.
To wrap up, Connor will go over standards and references.
These are the standards that applied to this project. The first one applied when the team was constructing the wind tunnel and using power tools. Safety goggles were always worn when applicable. The second one was incorporated as the system has an emergency shutoff switch. The only reference used by the team was high-speed wind tunnel testing by Pope.
We'd like to thank our contacts at Northrop Grumman, Sierra Rose, and Grant Senechel for making this wind tunnel possible. We'd also like to thank our mentor, Doug May, for leading us in the right direction. We look forward to seeing you at the University of Arizona on Design Day. Bear down!